So I wanted to kind of level set to kind of talk about where I'm coming from here. So I feel like there's been a lot of talk about containers from the perspective of using containers for HPC workloads. And in some ways, I'm going to talk about like the opposite, which is how HPC can help kind of the broader kind of container from the other side, which is like coming from the world of cloud computing, which is kind of where my background is, how we're kind of seeing the influence of HPC in that world and kind of how we can all work together. So a little bit about me. I've been involved in the Cloud Native Computing Foundation, or CNCF, for more than 5 years now. And recently, one thing I've seen, especially with the rise of AI, or specifically LLM workloads, is a lot of interest in putting GPUs into clouds so that container workloads can access the GPUs directly for AI inference and other types of workloads. I think this interest has started to kind of bridge the gap between folks working in the cloud and folks working kind of closer to the hardware on more of that performance-related pieces. And so my kind of argument today is that this is kind of an opportunity for both folks in HPC to get some of the benefits of stuff that's already been built in cloud computing, which I've already heard a bunch about today, which is exciting, and also for folks in cloud computing to get some more of the benefits of all of the kind of performance optimizations that all the folks in this room have helped build. So just to make sure we're all talking about the same thing, here's a kind of a simplified view of some containers running on a node. Very oversimplified, I know. You have a lot of different containers sitting on top of the kernel with some hardware underneath. And then you have mechanisms, things like namespaces, cgroups, seccomp, all these technologies that put kind of a barrier around the containers so that they can kind of act like independent units while they're still fundamentally sharing the same system, which then, is how the hardware interfaces with the different containers. One of the things that this model kind of promises to the software developer is the idea of hardware agnosticism, and that no matter what hardware your container is running on, no matter what cloud it's on, it'll behave the way you expect it to, always the same. Which sounds great in theory, but as you know, this in practice isn't always actually true. The performance can depend on what kind of hardware you have, what your storage backend is, how closely located are the different pieces of hardware that you're using. Different hardware obviously has different costs. Some of it is cheaper, some is more expensive, different performance characteristics. And because containers run in the host operating system, they have to be compiled for the correct CPU architecture, let alone other pieces of hardware that you have in the system. And this is not always interoperable. And I think this becomes even more true when you start adding things like GPUs to containers. You see things like NVIDIA building their own container runtime that only works with NVIDIA GPUs because there's so much that needs to be specific to the hardware all the way up in the container runtime. And so this kind of brings us to this idea of heterogeneous containers, which is kind of related to the idea of heterogeneous computing, but kind of bringing it up into this world of cloud computing. The idea here is that awareness of hardware can become a strength and not a challenge. This isn't a downside to having more different pieces of hardware available. This is a strength, right? This is an opportunity to use specialized processors the way they're meant to be used, for particular types of workloads. To use accelerators like GPUs or task-specific FPGAs, and really use the benefits of the hardware in the container stack. And this can also add things like improved security if we have hardware-backed cryptography and other pieces. We can also get kind of better, on the other side, we can get better utilization of the hardware. If you have a really expensive GPU that you've purchased and you're using it for a particular workload, wouldn't it be great to share that between multiple different folks who need access to that GPU for their particular tasks, but so that in a way that you can actually share the hardware both kind of practically and securely. And my kind of thesis here basically is that we're in a pivotal moment for this idea of heterogeneous containers. Because of this increased use of GPUs that we're seeing with AI workloads, this means that there's a lot of clusters, kind of folks in the cloud computing world, that are already becoming more hardware aware in order to support these specific GPUs. And so why not capitalize on this moment to kind of bring these two worlds closer together beyond just GPUs? That being said, I am going to focus kind of on GPUs as an example, and then we'll kind of focus back out, because this is, I think, where we've seen this start. And so one of the things that I want to talk about here is kind of the risks of this hardware access in the containers. So this idea of heterogeneity comes with some risks when you have multiple different containers running on the same system in what we would call a multi-tenant environment. So when multiple containers are sharing the system and have different users or different applications sharing the same hardware. So GPUs, for example, very expensive. In our kind of example I'm going to talk through for the next few slides, we're going to want to be able to share one GPU among multiple containers in this multi-tenant environment without the different containers being able to access data from each other. Yeah, because the data might include sensitive data, things like model weights, training data, customer data, anything you don't want all your friends sharing this infrastructure to also have access to. Maybe they're not your friends, I don't know. So we want to make sure that this data that you have on one container that's used on the shared GPU is not available to other containers. And the reason this is important basically is there's some evidence that, for example, changing a small portion of training data for AI workloads can change the result of a model in kind of dangerous ways. Or you can have one container trying to steal all the GPU resources for itself when it wants to, and then everyone else who's expecting to have it won't have access to it. So why is this hard? Why is this not already solved the way it's solved for CPUs in containers? And I think this is partly because of the design of GPUs and kind of how that differs from the design of CPUs. There's a lot of kind of process isolation and security features that exist in CPUs that aren't really designed into GPUs, because they're really designed first for processing massive amounts of data at once, and a little bit less for having multiple different users share the system. As some kind of examples of how this is true, there's no hardware page table that can partition memory between the different processes. It's all kind of in one box. A lot of GPUs don't even clear memory between workloads by default. So if you have two workloads on the same GPU, they basically have full access to memory of other workloads. And this can be a problem in this kind of environment. And this is kind of true regardless of what isolation practices are in place on both the CPU and kind of in the operating system kernel. Because those, obviously those don't affect what's happening on the GPU itself. So, and another example here is that GPUs can run overclocked or overdrive, which a lot of folks do to improve performance. But because this is not really using the GPUs as the manufacturer intended, it can improve performance, but it causes certain errors to be more common. And we've seen folks kind of be able to figure out which types of errors are more common and kind of exploit this to interrupt other users or get some data leakage and other things. And even worse is the actual bugs, right? So we're using GPUs, I think, in a lot of new ways these days with AI training. And this is just a small sample from the past year of vulnerabilities that cause things like privilege escalation, code execution, data leaks, crashes, things that you don't want happening to your application. The point isn't really that these vendors are bad at this. I think they're working really hard to solve these problems. But again, this is a new way to use the GPUs, and some of those security features and awareness of what happens around them is still catching up. And I think it's important that we use them in a way that even when stuff like this happens, it's not catastrophic. Because I think it probably will start to keep happening at least for the next few years. So what are our goals here? Our goals are to access a GPU from multiple containers, but maintain a way, have a way to maintain isolation between these workloads, even as the data moves to the GPU. And what we mean by isolation is that workloads can't access memory or impact the running of other workloads on the same system and specifically on the same GPU. And we want to achieve this in a resilient way that uses defense in depth to reduce impact, etc. And one solution here, and I won't go too much detail here, is the use of kind of PCI pass-through through a hypervisor. And the hypervisor itself actually adds kind of an extra layer of CPU-based isolation using CPU partitioning, basically, to separate those resources to the containers. And this can also help with the GPU partitioning, basically. So the kernel that you have per container here contains the GPU drivers, and the hypervisor kind of mediates access to the GPU for each container. So in the hardware, what this means is that we have the IO-MMU that acts as a translation layer to the GPU memory, and then the PCIe allows devices like the GPU to connect to perform DMA, all the way through. So this is kind of how the memory and processes kind of map through the stack. And one thing to note about this model is it's somewhat resilient actually to GPU CVEs, because the GPU only has one data from one container at a time. There are some other models, and I think various GPUs support, for example, like kind of software-based partitions of the cores in the GPUs and of the streams in the GPUs. But that does mean that you still have a bunch of data on the GPU at the same time. But that's kind of another way to approach this here. Running out of time, so I'll keep going. So what can we learn from GPUs in this broader picture of heterogeneous containers? And like how HPC and kind of this world of cloud computing can fit together better. So the first is that adding specialized hardware to containers has benefits for both performance and resource usage. Benefit for the performance of existing application and resource usage of the specialized hardware that you have, right? If it's ever, it spends less time sitting idle if it's able to be shared by multiple different processes on kind of a single system. But this requires multi-tenancy, which means that designer of heterogeneous containers need to think about hardware isolation in a way that's kind of new for the world of containers that so far kind of are really only good at isolating CPU-based workloads. So what does this mean kind of looking forward? So I think the introduction of GPUs to containers opens up kind of a whole new world of hardware and kind of HPC type optimizations in the cloud. Whether this is other accelerators, other specialized processes, or other workloads using the GPUs that we now have access to, right? In some of these bigger cloud systems, they're starting to add native support for GPUs for AI workloads. Who else can use these GPUs, right? This is kind of a whole new opportunity to use this kind of compatibility. And I think what we need to kind of get to this future and really utilize this moment is both more folks on the cloud side, more platform engineers, cloud architects, who are willing to dive into the hardware and into this world and see what's already here in this world of high performance computing. And also on the other side, we need folks, I guess I have this on the next slide. We need folks on the hardware side who are willing to kind of look into the cloud and figure out how we can apply some optimizations to workloads there. I've seen a lot of this kind of at work already this week, but I think there's more opportunities for large-scale cloud systems that already use hardware from all different vendors and a lot of different models, and kind of enabling this compatibility layer and making this all work together. I think we're just about out of time. So in summary, the shift to heterogeneous containers is a huge opportunity to achieve better performance, better hardware utilization. But to do this right, we need to ensure secure multi-tenancy, proper isolation of hardware resources. And I think this is really our moment to work together to make this happen, to kind of utilize this, this kind of excitement around AI to kind of build this broader support. So thank you all very much. And I think we are out of time, but I'm happy to hang out in the hallway for questions.
I don't know if they're going to kick us out, but there are no sessions after this at the end, so I think we can hang out here. If people have questions, raise your hand. I will run around a microphone to folks. Ryan, make them more part.
I'll start with a really easy question. Where can I get a Ocelotl sticker?
I might have some. Come find me after.
So one of the things that's come up in discussion just with containers and GPUs, among other things, is the issues that we have 3 different GPU vendors, not counting all the different CPU vendors and various features. Do you have any insight or comments about where the standardization of parameterizing containers so that we can choose the right one for the right hardware is going?
Yeah, yes, I think this is one of those opportunities I was talking about. I think right now there's a lot of each of the vendors is kind of building their own cloud stack, which in some ways is moving backwards in the world of cloud computing, where the idea is that you can have, again, this idea of hardware agnosticism, whether or not it's real. I do know there's interest in building this compatibility layer. There is work what's it called out of AMD, the open something, which is theoretically open source, but not really supported by the other vendors. And I think there's other folks doing this in a small capacity. I haven't seen a real coalition around a way to do this.
Thank you.
To continue on that question real quick while I make my way to Andy, Do you think this is an opportunity to amend something like the OCI spec to make registries more aware of different like GPU backends and such?
I think that's a great idea. I think, I mean, having worked with some of the folks in the OCI spec, I think it's hard to get changes through because their whole idea is stability. That's like their goal as a project. That said, I think it's a great idea. Yeah. Yeah.
So my question is actually related to that, in that in lots of forums around HPC, using containers and HPC, you know, containers excel in things that are standardized, right? With stable ABIs. And GPUs do not have stable ABIs. Yes. And MPI doesn't have a stable MPI. You know, open MPI notwithstanding, yada, yada. SPAC's ability to build anything on the head of a pin notwithstanding. So OCI hooks have been proposed as being one of the, I think kludge is probably the right word here. I mean, do you have a position on that in its ability to, their ability to smooth over some of the rough edges you point out?
I do think that there is an opportunity there. I think that, I mean, again, the idea of OCI is to have this kind of stable compatibility layer. And I think so far they haven't done that in the GPU space. I think maybe that could be, again, to answer the previous question again, that could be the place for that, right? The place for like an open standard. In some ways, I think it's more likely that we'll find a coalition, like a different open standard, and then the OCI adopt that open standard versus the OCI kind of creating that open standard. I could be wrong. That's just kind of the way I see, you know, the expertise in the different spaces. But
Really do.
Where do you, okay, so if you do optimize containers for different sorts of hardware, and I mean, this has come up in HPC for a while, what do you think is the right place to do architecture selection? Like, if I want to pick the best container for the hardware that I'm on right now, who's responsible for that? The runtime, the launcher, and OCI? Like, where does it go?
yeah, I think this is one of the challenges. 'Cause I think what would be great, right, is if there could be some sort of automated way to figure out what the right system for each thing is. In the end, I think what people end up doing is just a lot of kind of performance testing on different systems, and then for each independent workload, which is definitely not the ideal solution. Yeah, that's not a very good, compelling answer, sorry.
Okay.
Okay, if there are no more questions, then I guess I will let everyone get to the reception. Let's thank Marina one more time.